Hi students, welcome to my lectures on mechanical unit operations. Today we are going to discuss about a topic called flow past immersion objects. What this means? Flow past immersed objects. When the particle is moving inside the liquid, there are number of forces that is going to get created. And studying of these forces is called through this when the inflowing conditions or still conditions. So then it is called flow past immersed objects. The main important, there are three major forces that acts when the particles are moving in a fluid. It could be air, it could be water, it could be oil. The three main forces are, imagine a bucket of water. If you drop any stone or any object into it, it travels through the water. During its travel, it experiences different forces. The one is gravity force, second buoyancy force which is upward, drag force which is upward, and gravity force which is downward. That means two forces that are acting upward direction, one force is acting downward direction. The two upward forces are buoyancy force and drag force, and one downward force which is called the gravity force. That's what in this chapter we are going to discuss, majorly about these three forces. Okay, that's why there is direction I have given, that two upward forces and one downward force, and Fg is called gravity force, Fb is the buoyancy force, Fd is the drag force. Let us see. I have something to show you. Today I am going to later part of the video. I will show you how to exactly calculate these forces. So to physically see how the forces look like, let us go to the some experimental lab, and I'll show you all these forces. Students, you have two containers here. Both are filled with water. So both contains still water, means water is not moving at all. That's called the still conditions. The moment I add pebbles, you can see because of the action of the forces, the particle will come down. I told you there are three forces. One is the gravity force, and the two forces that acts opposite to the gravity, one is buoyancy as well as the drag. The drag in still conditions are very low, because if the water is moving upward direction, then the pebble is moving downward direction. In such condition, the drag will be very much high. At this point, the drag is very low, and you know what is the gravity force, m into g, you can able to calculate. The one on the other container here, you can see I have some polystyrene foam which I am trying to push the things inside. I can see because of the force, it is the buoyancy force. This is called the buoyancy force. The more is the, see, when I push the polystyrene foam into the water, the more is the volume I am putting in, more is the force I am experiencing. If you release your hand, it will pop up. You can see it will pop up. This is called the force which I feel here by displacing the water. You can see how much force I can calculate, because imagine this is the amount of water that is displaced because of the polystyrene foam that I have put it inside this container. That means more is the depth I am going to put it inside, more is the volume of the water it is getting displaced. So more is the buoyancy force I can generate. Less is the water displaced, less is the force. More is the water displaced, and more is the force. This is called the buoyancy force. In the board, in the next part of the lecture, I will show you how to calculate this as well. And this is the third one, which is called the fluidization assembly. In this assembly, you can see all the three forces acting in a container. Here, and I have a beaker which is filled with a sand, graded sand. All the sand particles are of equal size. Okay. Now the bottom, I have one inlet at the bottom, outlet at the top. The moment I pass the water with certain velocity, what happens? The drag is going to get increased. Okay, if drag is going to get increased, the sand particles will be lifted. Okay, after certain height, you can observe, I mean, the sand, which is a solid, now behaves like a fluid. That means it will have the fluid kind of property. It will move along the entire the container because it has many industrial applications, because the fluidization has a many industrial applications. We will see at the later what are the different applications as such. Let us see. I try to increase, I mean, if I start flowing the water from the bottom, see what happens. I have marked the initial length here, which is at the black, is because this is the length of the bed. Okay, from here to here. Let us see what happens. After certain point of time, you can see the bed has been lifted. Now you observe this. Okay, if you observe, now the sand particles are behaving like that of a fluid, and bed height also got raised. Why the bed height got raised? Because the particles now before the start of the experiment, all the particles at a very close distance. As I increase the flow, the particles, there is the spaces between the particles which is filled up by the fluid. Now this is called, you can see the particles are trying to come down, but the drag is trying to lift up, and buoyancy is also trying to lift up. So this is the important I mean application of the fluidization, because there are many other applications. You can see more, if you surface area also available, because the particles get separated, more surface area will be available. So the moment if you keep a velocity which is higher than the fluidization velocity, what happens? The particles will go to the outlet, because I have maintained certain velocity so that the entire bed is in the fluidized condition. So this is how, and because of this application, you can transport solid from because beyond the fluidization. If you go, that's called as pneumatic or hydraulic conveying as such. Okay, this is what. Let us go to the board and discuss how to measure this kind of drag, I mean gravity and buoyancy forces. Let us calculate how to see how to calculate the gravity force, because I have a certain object. Okay, what is how my gravity force is equal to mass of this object into gravity. So mass of the object I have measured is around 250 grams, and gravity is equal to 9.8 meter per second square. Then if I calculate, then gravity force is equal to 2.45 newtons. Similarly, if I want to calculate the buoyancy force, this is what the trick lies. The buoyancy force can be calculated by Fb is equal to mass of the water that you have to take into consideration, because the moment you put the object in, it will displace some water. So you have to calculate how much mass of the water getting displaced because of this object that is getting immersed inside. So buoyancy is equal to mw into g. Mw, mass of the water displaced by the object. Imagine this is a container. I have immersed a certain object which is having length, breadth and height 3 centimeter, 3 centimeter, 1 centimeter. Okay, then in such cases, what is my buoyancy? Volume of the object is equal to 1 into 3 into 3, 9 centimeter cube, which is 9 into 10 power minus 6 meter cube. Mass of the water displaced you can get by volume into density of water. What is the VO? Volume of this object, because this is the volume that is getting water got displaced. That means if you directly take entire volume of the object, that means that much amount of water is getting displaced. So VO is the volume of the object multiplied by density of the water. So 9 into 10 power minus 6 into 1000 kg, and you get mass of the water is 0.009 kg. Okay, you know the mass, you know the gravity, you multiply these two things, you get 0.009 kg into 9.8 meter per second square. This comes to be 0.0882 kg into meter per second square. Okay, but the buoyancy force is equal to 0.0882 newtons. You can compare the number. It's a 2.45 gravity force. Buoyancy force is equal to 0.0082. Let us see how to calculate the drag force. To calculate the drag force, you have to use this formula. Okay, CD drag coefficient, AP is the projected area of the particle, density of the fluid, U, velocity of the particle relative to the fluid. Example, if the particle is moving in this direction, the water is moving in the opposite direction, the difference between these two velocities is called the relative velocities, okay, and divide by 2. Assume this is the particle, I mean the projected, if a particle is going in this direction, the projected area will be this one, okay, because this is the area that is being dragged, okay. So this is called projected area. For my particle, assume this square particle kind of 3 centimeter projected area and 9 centimeter square, that is called this much amount of meter square. CD, this is called drag coefficient. Drag coefficient is nothing but kind of a friction factor. In pipe, you go with the friction. When the particle is moving inside the liquid, that's called the drag. That is the difference between the friction factor and the drag coefficient. Drag in laminar conditions, it's a 0.44. In turbulent conditions, there are certain graphs and equations are available, I mean to calculate the drag coefficient. Okay, assume this is a laminar conditions there inside the chamber. In such cases, CD equal to 0.44 you can take. Density of the fluid is 1000 kg per meter cube. Velocity, I have measured how much velocity the particle is getting down. Imagine if I know what is the velocity of the particle, then let us be 1 mm per second, that is the velocity of the downward velocity of the particle, this is a settling velocity, that's a 0.001 meter per second. Substitute everything in this equation, you get 1.9 into 10 power minus 7 newtons. You can see the drag force is 1.9 into 10 power minus 7 newton. The highest force is gravity. For this mass, for this buoyancy is equal to less than the gravity, drag force even less than the buoyancy. So that is why effectively the particle will come down, because more is the gravity, less is the buoyancy and the drag, so the particle will come down. As the particle becomes smaller and smaller, the mass of the particle will reduce compared to the surface area of the particle. In such cases, more drag it can experience, okay, because at this example, this is what I have given, this is the chamber. I have pumped the water from the bottom, taken water from the top. The particle which is inside will experience these 3 forces. Depending upon the magnitude of 3 different forces, it will decide that the water will come down or go up. If you use more velocity of the water, what happens? The drag force will increase. So if the drag force dominates the gravity force, and what happens? The particle will come out of the chamber. So always the balance between these 3 forces decides, okay, the fluidizing conditions inside the bed. I hope you have learned something useful, and I'll come back with a new video. Thank you very much.